Hello, hello, all you chemistry nerds out there. We are back, and I hope you didn't do anything with your molar map thinking we were done with it, because we aren't. We have some stuff to add, and we are going to be adding molarity. Not the kind of moles that are in your teeth, but the kind of moles that are in all of chemistry. So if we think back to what we've gone over so far with stoichiometry, we have done just one reactant or one product and then taken it to another product or reactant. Remember, you only have to do stoichiometry once if you're only given one. If you're given two reactants and asked for a product, you have to do stoichiometry twice to find the limiting reactant, and then it's the lowest amount of product that you can make is the one that's limiting you. And if you're asked for your percent yield, remember that it's your actual over your theoretical times 100, and your actual comes from an experiment, theoretical comes from stoichiometry. So we are still going to be using these steps, but we're going to be adding something to it here. So if you think to your mole map, gases are the only thing right now that we have measured in volume. But you might be thinking to yourself, there's lots of other things that we measure in volume. Like when we're in the lab, we measure liquids and acids and all this other stuff in volume all the time when we use a graduated cylinder. And you would be correct. Liquids and gases are both measured in volume. And so we need a new path. We need to be able to convert gases to volume, but we also need to be able to get to liquids, or from liquids to moles. And we use molarity for that. Molarity is just a big M, is symbolized by a big M. So all molarity is a measure of the concentration of solutes dissolved in liquids. Okay, so if you think about it, I know I like to go home on the weekends and tip me back some nice old cold Kool-Aid. And some of you might like your Kool-Aid almost to the point where it's syrupy. You put so much sugar in there that it's so sweet and you can feel your teeth rotting when you drink it. Well, if you put lots of sugar in it, that's a very high concentration of sugar that's in your drink. That would be a high molarity. High concentration, high molarity. If you're like me, I don't like as much sugar. I like mine a little more sour, so I don't put as much sugar into it. When I don't put as much sugar into it, it has a very low concentration. A low concentration of sugar would be a low molarity. So all we're looking at here is the amount of stuff that's dissolved in it. If there's not very much stuff, then it's going to be a low molarity. If there's a lot of stuff dissolved in it, it's going to be a high molarity. And this can be said about anything that we dissolve in water. Salt, sugar, anything, acid. So when we're looking at how we figure out what the molarity is, all we do is take the number of moles that are in it and we put it over the liters of solution. It's just moles per liters. This is something big to keep in your mind right now. Moles over liters. That's all it is. So remember, as we do this, everything except your mole-to-mole ratio is going to be 1. When you divide your moles divided by liters, liters becomes 1 as well. So it's the number of moles of solute per 1 liter of solution. Now when I keep talking about solutes and solvents, all I'm saying is the solute is a substance being dissolved. So it might be salt that we're putting into water, or it might be hydrochloric acid that we're putting into water. Whatever's going in and going to be dissolving. The solvent is the liquid doing the dissolving. Most of the time this is going to be water, but not everything dissolves in water. If you think back to polarity, like dissolves like, some things might dissolve in gasoline, or some things might dissolve in oil. So it just depends on their polar properties of what our solvent is going to be, what we have to dissolve it into to get it to dissolve. So again, molarity is abbreviated capital M. Please make sure that you're using a capital M. Don't get this confused with a small m, because small m means something different. So capital M is equal to the number of moles per 1 liter. So for example, if we have a 1 molar solution, that means we have 1 mole of dissolved stuff in 1 liter of solution. So it would be like taking 1 mole of sodium chloride, which would be 58 grams of sodium chloride, and pouring it into 1 liter of solution, stirring it up. A 2 molar solution means we have 2 moles in every liter. So it'd be like taking 2 moles of NaCl. If 1 mole of NaCl is 58 grams, 2 moles is going to be around 116 grams and putting it into one solution. We're just taking the number of moles per liter of solution. So we will, in class, add to our maps here, but we will be adding this pathway. To get from moles to volume, we use molarity, moles over liquids. Okay, so now we'll have to distinguish what type of volume we're looking at. Let's try an example here. If we wanted to know the molarity of 4 moles of KCl in 2 liters of H2O, remember that all molarity is the number of moles over our liters of solution. Now we won't always be given 1 liter of solution, but when we put these two numbers over each other and divide, it's like finding a ratio for every 1 liter. So our number of moles is 4, our number of liters is 2. If we put those over each other, we would get 2 moles per liter. Notice that none of our units cancel out here, so we're left in moles per liter, which is 2 big M, or 2 molar. How about this one? What is the molarity of 3.5 moles of calcium hydroxide in 100 milliliters of solution? Well, this one is a little bit different because it gives us milliliters instead of liters. In order to have molarity, we have to have it in liters. So we're going to have to convert here. So if we start out by putting our moles over our volumes, 3.5 moles over 100 milliliters, we need this bottom unit to be liters. So we can just convert to do that. We know that there's 1,000 milliliters in 1 liter, so our milliliters would cancel out, and the units that we have left are moles over liters, which is equal to big M. So again, multiply across the top, divide across the bottom, and you get 35 molar, or 35 molarity, big M. Units are always in moles per liter, so you might have to convert in order to get it to that. Let's try another one. What is the molarity of 64 grams of sodium chloride in 580 milliliters? Okay, so this one, we aren't given liters and we aren't given moles, but we know how to get each of those. So if we start out by putting our 64 grams over our 580 milliliters, we always know that we have to have a mass or moles over our volume. Then we can convert to get the units that we want. So 64 grams, we know on top here has to be moles. So we can go from grams to moles using the molar mass. Grams of NaCl are going to go on bottom and cancel out, and moles of NaCl are going to go on top. Remember that this comes from the periodic table. So now our units are moles over milliliters. We need it to be moles over liters. So again, we can convert. If we do one more step here and go milliliters to liters, our milliliters cancel out, and the units that we're left with are moles over liters. Multiply across the top, divide across the bottom, and you get 1.9 big M, or moles per liter. Again, make sure your units always end in moles per liter. Is it burned into your brain yet? Okay, let's try another one here. Let's try putting stoichiometry in with our molarity, or vice versa, molarity in with our stoichiometry. So we are looking for what volume of HCl, so we want to know the volume here, is needed to react with 3 grams of NaHCO3. So we are going from grams to volume on our map, starting down here, going to volume of something different. So, starting with what we know, we're going to have to go grams to moles, and then moles to volume. So, 3 grams of NaHCO3. Grams to moles, we use our molar mass that comes from our periodic table. So our grams of NaHCO3 cancel. We then go mole to mole, and in our balanced equation up here, I gave it to you balanced by the way, we have 1 mole of NaHCO3 to 1 mole of HCl. This is the same reaction we did in the salt lab, where we made baking soda into salt using HCl. The same thing that happens in your stomach when you take an antacid. So our moles here are going to cancel out, and now moles to volume. And to get from moles to volume, we know that HCl is a liquid, so we're going to use the liquid path, not the gas path. So we know that there are 2 moles for every 1 liter. We're in moles of HCl, so our moles have to go on bottom. 2 moles of HCl. That will cancel out, and we're left in liters on top, which is a volume. So if we calculate that out, we get the answer, but I hope you got the point. Sorry about that. All right, let's do one final example here. How many grams of NaHCO3 will react with 55 milliliters of 1.5 HCl? So if we have grams of NaHCO3 that we're looking at for, and we have 55 milliliters of 1.5 molar HCl. So we know 2 things about the HCl. But think back to your mole map. The only places that we can start are these big ones. Molarity is a pathway, so we can't start there. We have to start with our volume. So starting with our 55 milliliters of HCl, we'll have to go volume to moles, moles to moles, and moles then to grams. So if we start with our 55 milliliters, our pathway involves moles per liter, so we have to convert milliliters to liters. 1,000 milliliters in every 1 liter. And then we can use our molarity, because molarity is moles per liter. We need our liters on bottom. We always have 1 liter, and we have 1.5 moles of HCl. So 1.5 moles for every 1 liter. Liters cancel. Once we're in moles, we can go mole to mole. Again, our mole to mole ratio in our equation is 1 to 1. So moles of HCl, 1. 2 moles of NaHCO3, which is 1. And our last step is to go to grams. So using the periodic table and the molar mass, moles of NaHCO3 is 84 grams, and we are left in grams. To get that answer, multiply across the top and divide across the bottom. Okay, so this is the same process that we've been going through for stoichiometry. We're just adding that one step in case we have liquids. Again, if you have any questions, let me know. Otherwise, we will practice this a little bit more in class. We'll see you then.